Okay. Thank you very much for Arigenser for giving me opportunity to be here. Just I want to present this paper. So this will be devoted into several iron-based compounds. It will be most simple iron, selenium, tellurium, and a sample which intercalated with rubidium and intercalated with organic materials. So if you have this most simple material, this is iron, selenium, tellurium, you have just transition depending on the concentration of selenium and tellurium. However, if you look literature, there is some statement that this material with composition selenium 0.35 has highest crystallographic quality. What it means? Basically, you have the situation like this, that you have tetragonal host lattice, and in this tetragonal host lattice, they appear some area with some hexagonal area. So in this tetragonal lattice, you have some hexagonal area. So this is what means that this crystal is not perfect or something like this. And if you grow single crystals, you can just play with this, because you can just play with speed of growing of crystals. And if you play with speed of growing of crystals, you can get basically a slightly different X-ray diffraction picture. Here they are example of several crystals which were grown with a different speed, and the difference between them is the width of this peak 0.04. And if you compare superconducting state properties of these crystals, you can find huge difference. They are basically the nominal composition of the crystals is identical. You can see here as very sharp transition here, and you have very well developed heat capacity peak. But in another case, in the crystal which was grown in slightly different conditions, you can find that superconducting transition is very wide, and the peak in heat capacity is almost not developed. So we just decided to put all of the crystals which we grow in one picture, and just to compare with width of 0.04 crystallographic peak. And we found that if the peak is very wide, the transition temperature is extremely sharp. But if peak is very narrow, the transition temperature is extremely bad. This is something which is completely opposite what we have intuitively. Because intuitively you think that if you have very high crystallographic material, very high quality crystallographic material, it should be very good superconducting materials. But this result is completely opposite. So we just decide to perform transition electron microscopy, and this is so-called scanning transition electron microscopy high annual dark field. And this crystal, it is the crystal which is grown with very high speed. This crystal is grown with very small speed. So you can see that in the crystal which is grown with very high speed, you have a lot of hexagonal phases which are distributed everywhere. If the crystal is grown with very low speed, these hexagonal places are very well developed, and they are separated. So the difference in this is that in this material you have a lot of boundary between tetragonal phases and hexagonal phases, and this one you have very small boundary. So our conclusion of this work was that if you have materials with bad crystallographic quality, very homogeneous, it show very good superconducting state properties. And so we decided to perform transport measurement for such materials. This is crystal which is grown very fast. This is crystal which is grown very small. This is millimetric paper. You can see difference. There, if you make extension of this picture, you can see here. And just the paper was published a few years ago. And just by making of bridges, we put current, and we found again that this crystal, which it is grown crystal, which is grown with very big speed, very fast, and this crystal which is grown very slow. So you can see this is more or less what I showed you already. But here there is the difference in critical current. So you can see that critical current, and this one, it is just a boundary or just ages of the crystal which was grown with a slow speed. So it is something between a crystal which is grown with high speed and low speed. And this is just a critical current, so this is a quite huge difference of critical current. So this is again that bad crystallographic quality means that good superconducting state properties. But I show you the results which are obtained for the crystals which are grown with different techniques. So somebody can say, okay, you see, this is not exactly the same material. You grow with different technique. Maybe you have some substitution, or maybe you have some difference in stoichiometry. So we try to find a material which will be more convincing, and this material, it is rubidium intercalated iron selenium. So the crystal formula is rubidium iron 2 minus X selenium 2. For such materials, there is a scanning transition electron microscopy image. You have basically you have two phases. One phase is, for example, rubidium 0.5 iron 2 selenium 2, but can be rubidium 0.5 iron 1.6 selenium 2. And you can see this phase is scanning transition electron microscopy image. And so there are, here it is a description how the crystal is grown, but this is this is for technique. If somebody want to repeat measurements, they can look at details. The most important is that just growing these crystals, you can get this several two phases, at least two phases of materials. And if you perform measurement of temperature dependence of heat capacity of this material, you will find that they are basically three transition. This is a phase separation transition. So this is this is structural transition here. So at this temperature, this is this structure which is responsible for superconductivity appear. Here there is null temperature, but here is a phase transition temperature. And in this region there is only one phase, but the two phases appear in this region. So the idea was that let's try to anneal this sample in phase transition temperature, just the same crystal which was grown, just anneal at this temperature, and try to check this amount of phases, this one phase to another phase, and just to check if there will be any superconducting properties, change of any superconducting properties observed. So here there is just description what was done, but it's also not really important. This is just annealing at phase transition temperature. And here there is picture, and this picture clearly shows that this is an annealed sample, and this sample is annealed in phase transition temperature for 0 hours. It is this one, and this one is annealed for 3 hours in phase transition temperature. So So this is this annealing temperature. But just to check if there is no some crystallization or something like this, we decide to anneal it also in different temperature. Temperature slightly slower than phase transition temperature and slightly bigger to phase transition temperature to see if this is a result of a really rearrangement of phases in material, or it is something additional. Here there is magnetization curves, and you can see that the crystal which is annealed in phase transition temperature has much sharper transition temperature. The difference between these curves is time of annealing. Here there is initial magnetization curve also, and here there is resistivity data. You can see also that resistivity is changed quite much, and here there is upper critical field, and you can see significant change. So we can find that we can just change superconducting properties by annealing, but we must know what it means. So in order to know what this means, we performed mu-SR measurement, and the most important picture is probably this one, that the sample which was annealed show very homogeneous magnetization inside of the samples, but this magnetization in the samples became much more inhomogeneous after annealing. So this is again mu-SR measurement, and these changes observed by mu-SR are correlated with changes of scanning transition electroscopy image, and so this is a conclusion of our work that both mu-SR and scanning transition electron microscopy investigation show that as a result of annealing, there is non-magnetic regions in the sample arranged in this way that as a result of annealing they became much smaller. The amount of them is identical, but they became much smaller, and because they became much smaller, you have just strong higher changes of magnetization in space, because the material is much more inhomogeneous. So again, we get the conclusion that bad superconducting properties means bad structural properties means very good superconducting state properties. So the question is that now we know about this kind of materials. So let's try to see what will happen when in nictides intercalated with organic materials. So this is just general picture which show how intercalation works. So you can get increase in the material which was when was with rubidium it was about 30 Kelvin. Now you can get 46 Kelvin or something like this. However, you must know that also the superconducting properties of this material are not more ideal, and you can have in such materials some ferromagnetic impurity or something like this. So you can see that, for example, this is just field zero field Coulomb magnetization. Of course, there is transition about 40 Kelvin, nice transition, but still you have some background signal. And we decided to measure for this material HC2. The measurement of HC2 were done in this way, that the sample was warmed in a constant magnetic field, and just appearance of a constant signal, which is temperature independence, was considered as upper critical field. And we found for these materials that upper critical field behave in such a way. So up to, let's say, 30 Kelvin, we have very strong very high upper critical field, which is quite similar for rubidium intercalated compounds. However, for the higher temperatures, there is this much smaller upper critical field. This upper critical field still exists, but it's much smaller, and this is just somewhere where here there is a transition to non-superconducting state. And we performed several hysteresis loop measurements, and we found that then in these materials there is very narrow hysteresis loops in the temperatures above 30 Kelvin. So we assume that in these materials we can increase quite much transition temperature, but this is because we introduce into material some kind of magnetic inhomogeneity, and this magnetic inhomogeneity playing the same role as structural inhomogeneity, which I will show you in rubidium materials, rubidium intercalated materials. So my conclusion, it is very simple, as I showed you this conclusion through full of paper, that high crystallographic quality, it is bad superconducting state properties. This work which I show you, it was summary of work which was done by several years. There was involved several people from the Institute of Physics of the Polish Academy of Sciences. I put in the author's name only the name of three of them. They are people from Warsaw University of Technology. The crystals grower were Nakstoin, Maziopa, and Dariusz Gawryluk, but the rest of people are Jan Finowicki, Berkowski. They were also crystal grower, and these people were responsible for characterization, structural characterization of people. They are also people from Polscher Institute, from ETH Zurich, and from Zurich University. These people from Polscher Institute are responsible for Muesser measurement. I would like to thank you very much for your attention. I hope I will in time.
Thank you, Roman, for this talk. This conclusion is very puzzling, strange, because we are used to think that the best crystals have the best superconducting properties. But I wanted to ask you one other stupid thing. But when you intercalate the iron selenium with these organic molecules, does it change also the mechanical properties, or it remains more or less the same? And this intercalation is stable with time or not?
There are several technical details which I didn't show. So the materials is made like this, that the intercalation is not stable at time at all. So the material is made like this, that just immediately after intercalation is put in quartz tube. And in this quartz tube, inside of this quartz tube is quartz rod, and quartz rod, the sample is put in quartz rod, and there is another quartz rod. So the sample completely fixed, and quartz tube is closed. And this sample is never in air. All of the time is in quartz tube. It's never removed. So all of the measurements are just for this intercalated material, only the magnetization measurements, because we were afraid to remove. And if you repeat this measurement after maybe 1 year, you will get still the same measurements. So I think the sample is not destroyed in this way. Even with a rubidium sample, we performed it because it was annealing. So all of the measurements were performed in the same way. The sample was in quartz tube with quartz rod, and the position was were fixed. But in rubidium, you can perform room temperature measurements. So transport was when sample was removed, but the sample which was magnetically measurement, it was all of the time it took. And concerning your comments, I understand, but you see, for example, every people which make iron-based superconductors, if they make polycrystalline sample, they have very high quality materials, superconductivity. But if they start to make single crystals, a lot of problems appear. So this is first and about naive idea about relation with quality of crystals. And still you can think that if you have some inhomogeneity in the material. There's not inhomogeneity, but it is inclusion. But there is, for example, hexagonal structure and tetragonal structure. So you can you have some stress between material, and this stress, the superconductivity might be just in the boundary, or just because of the stress, or just because of inhomogeneity. Crystal is you can make like this, that when you make intercalation, you put in quartz ampule tube. You remove oxygen. So this is just sample is or in vacuum or in argon atmosphere. And later you are putting in squid magnetometer. So during the measurement, this sample is measured in squid magnetometer. But because this is quartz tube and inside is quartz rod from both sides, so still material is quite homogeneous. So you can perform squid measurements. You needn't keep sample frozen for infinity. You cannot heat sample to high temperature, because if you will heat sample to high temperature, sample will become non-superconducting. But as long as sample is in quartz tube, you can keep sample in room temperature, and sample still is superconducting after 1 year or 2 years. There is no problem to keep superconducting properties. Of course, if you put in air, just it will be just because of oxygenation, so sample will become not anymore superconducting. So you cannot put sample in air, but you needn't keep sample frozen for many years.
Okay, thank you very much. So now it's almost time is up. So thank you very much for
Thank you.